Bam! Mr. Taru, in this calculus lesson, we are going to be taking a look at 4 examples involving the integral test. The first example is going to be one where we do the nth term test and make sure that the limit as n approaches infinity of a sub n is actually equal to 0, opening the door for the possibility of that series to converge. It turns out it's going to diverge. It's not too difficult of a question. The second example, though, is going to be a series that we're going to prove with the integral test does converge, and to give us a little bit of challenge in our review and with our examples, that will involve integration by parts and a little bit of L'Hopital's rule. So it'll be a somewhat involved example to help you along with your homework. And then our last 2 examples are going to go very, very quickly, because we're just going to remember that before we try to apply an integral test or any of these tests that we're going to learn in this chapter, and when we're looking for whether a series converges or diverges, of course, let's just make sure that we do check the nth term test to make sure that the limit of a sub n is equal to 0 as n goes to infinity, right? Save yourself some work. This section in our textbook also includes the p-series test. I'm going to have a link to that lesson in the description just as soon as it is done. And hopefully by the time you're watching this, it will be. The integral test: if f is positive, continuous, and decreasing for x is greater than or equal to 0, and a sub n is equal to f of n, basically what we're seeing here is we're going to be doing an integral test. So we're going to be setting up let f of x equal a sub n, so that we have some kind of function that we could lay down on a graph on top of the graph of the sequence, and everywhere that n is a positive integer, the domain of our sequence is, the function is going to have the same value or agree with the terms in our sequence. So if that is the case, then the series of a sub n, or the summation of a sub n from n going from 1 to infinity, that series, and the definite integral from 1 to infinity of f of x dx, those are both going to either converge or diverge, because, well, they're very closely related. We have a sum of a series and we have a limit of sums. Or looking over here again with our picture, I've got some blue dots showing values that we have in a sequence that ultimately, adding up, letting that n go to infinity, talking about that series, right? And does that series converge or diverge? Well, when we lay that function f of x on top of it that agrees, that our f of n is equal to a sub n, we can look at the integral. And we have some inscribed rectangles and some circumscribed rectangles. That idea way back in a textbook I teach from chapter 4, when we first started learning about integration and estimating areas bound between a curve and the x-axis using a finite number of rectangles, partial sums with our sequences. We have the idea that we have the summation from 1 to I starting at 2 going to n of f of I is equal to this inscribed area. We have the summation from I starting at 1 and going to n minus 1 of f of I is our circumscribed area. And somewhere between the lower sum and the upper sum, we have the definite integral from 1 to n of f of x dx. So just trying to tie in the idea that, yeah, we can look at determining whether a series converges or diverges and actually do it with an integral. It might be bothered a little bit here when I'm not doing the full proof, I'm just trying to give you this visual and these statements to help you relate the series and the definite integrals together, that when we talked about estimating area with a finite number of rectangles, we had some kind of f of I notation, and then there was a delta n, the widths of the rectangles, because of course our function is going to give us the height. But with the domain of our sequences and series being positive integers, the widths of these rectangles are always going to be 1, and that's why maybe you don't see a delta I here, not delta n with these notations that you might have been remembering that you saw when you first started looking at Riemann sums and estimating areas when we first started building the foundation of definite integrals, which of course doesn't always, actually often doesn't apply to area, but that's how we first started building that understanding. So here we go. Let's get to our first example right now. So for our first example, and I must apologize for the sound quality of the first part of this video, I'm actually shooting every example over. I don't know what happened with my camera, and it's working with my wireless mic system, but hopefully this works with my backup camera. We're going to, let me read the directions since I'm kind of now sort of reshooting all this. Confirm that the integral test can be applied to the series. If yes, then use the integral test to determine the convergence or divergence of the series. So in this example, I didn't really actually give us a notation for the series. I'm just simply giving us sort of an expanded version of the series where the first term is 1/4 plus 2/7 plus 1/4 plus 4/19, so on and so on with the little dot, dot, dot. So we are talking about adding for basically forever an infinite number of terms, thus it's a series. So that means that we need to take the n values of 1, 2, 3, 4, 5, and so on, and come up with an nth term, just like we did when we first started reviewing sequences. Okay, well, it looks like the numerators are matching the values of n all except for this third term. Well, at one term, that third term seems to be standing out, so if the numerator and n are matching for every single one of the first 5 given terms, then maybe we can just come in here and multiply this fraction by an equivalent value of 1 and make it 3/12. And just to save space, even though that was not much room before because, well, I had a big set of directions on here, and now I'm just hoping that this video works, we have 3/12. I don't know if you're a regular watcher of my videos, but I've been posting a lot of videos about sequences and series. This is my older camcorder, my Canon camcorder that I used to use making my YouTube videos, and now I use a Nikon DLSR, or maybe it's starting to not work very well. If you happen to like the quality of this video better than maybe the one I just posted last week, give me a feedback below. Okay, so it seems that we have an a sub n term of, well, the numerator now is a match n, and so on. And by the way, when you come up with an nth term expression, it doesn't mean that's the only answer. Someone else can come up with another a sub n expression that gives those values in the sequence, or in this case, because it's infinite addition series, and it still work. So this is a version, or one of the possible nth terms maybe. Now, how do we get those values of 1, 2, 3, 4, and so on to give us the values in the denominator? If you want to give that a shot, just pause the video and try it for yourself. It does take practice to be able to get these a sub n terms, but just to not languish here too much, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. Every time I take one of these n values, I'm 3 units, or 3, I need to add 3 to it to get our denominator. So we have a sub n is equal to n over n squared plus 3. So that means that our series is going to be the summation where n starts at 1 and goes to infinity of n over n squared plus 3. Great. Well, can we apply the integral test? Let's not worry about trying to apply the integral test unless we first make sure to do the nth term test. I mean, can we just let n approach infinity and prove that a sub n is not equal to 0, thus this thing absolutely positively diverges? Well, depending on, this is, hope by now we're probably not expecting too much work with these problems. The numerator has a degree of 1, the denominator has a degree of 2, so this is going to approach infinity. As n approaches infinity, this expression is going to approach, the a sub n term is going to approach 0. That doesn't mean the sequence, that doesn't mean the series converges, but it definitely, if this were not equal to 0, would guarantee that it would diverge. So this means that, let's go ahead and continue on. Okay, we can divide the numerator and the denominator by 1 over n squared, or we can apply L'Hopital's rule because this is infinity over infinity, past the condition check. But at any rate, we do have a series that may converge. So let's go on to that integral test. We're going to come over here and we're going to let f of x, don't forget to say let f of x, equal x over x squared plus 3. Now I'm going to try and not remember if I've said something or not in the intro because I've shot this entire video. But we're setting up that function, that f of n, that agrees with a sub n anytime n is a positive integer. And this needs to be positive. Okay, well, if you're letting x represent basically n, then, well, you know, this is a continuous function. Really, we're really interested about when x is 1, 2, 3, 4, 5, and so on. So this is always going to give us positive answers. It's continuous. The denominator is never going to be equal to 0. And even if it was possible for this denominator equal 0, that wouldn't be a problem, and there won't be a problem as long as it's not somewhere you know, along our domain that we care about as far as this series. You know, like if it was undefined at x equals -2, you know, not a problem. So we're going to find the derivative of f of x. It's going to be low to high. So we're looking at x squared plus 3 times 1 minus high to low. And the numerator is x. The denominator, the derivative of the denominator is 2x. Over low, x squared plus 3 squared. Okay, so we're looking at x squared plus 3 minus 2x squared over x squared plus 3 squared. 1 minus 2 is -1. Now, is the first derivative negative? Is this function monotonic decreasing or non-increasing? The denominator is always going to be positive. All we have to do is see where the numerator is going to be less than 0. Subtract both sides by 3. Divide both sides by -1. Square root. And x has to be greater than the square root of 3, which is 1 and change. So we have a derivative which is negative for when x is greater than or equal to 2. Now, this original series, we're trying to determine if this diverges, you know, where n starts at 1. But the first few terms in a series does not determine or influence whether or not a series converges or diverges. So it's not an issue that we have a first derivative that's decreasing or negative, you know, once you get to 2 and beyond. That's not an issue. Divergence and divergence is about what happens as n approaches infinity. So that is not going to be an issue, which means that we have f of x is positive, it's continuous, and it's decreasing as long as x is greater than or equal to 2. That means we can apply the integral test to see if this thing converges or diverges. All right, let me get this out of the way. Just make sure I have plenty of room. And we have the definite integral from 1 to infinity of, don't know really why I'm using parentheses, x over x squared plus 3 dx. Okay, because a fraction bar is a grouping symbol, so really no reason for another set of grouping symbols. The denominator has a degree of 2, the numerator has a degree of 1, so we probably can make a u prime over u situation show up. And so if we let u equal x squared plus 3, then du is going to be 2x dx. And I don't want to go through a whole u substitution. I just want some kind of scratch notes over here to the side, because I don't want to change the lower and upper limits if I don't need to, because this is a very easy chain rule to finish. I just need a 2 in the numerator, so let's go ahead and introduce that. If I'm going to introduce a multiplication of 2, of course we need to balance that with the division of 2, and here we go. We have u prime over u. Well, the integral of u prime over u is the natural log of the absolute value of u. Excellent. Now, don't really need the absolute value symbols there because, again, x is, well, we have x squared plus 3. That's always going to be positive anyway. And this x is really representing and working, we care about working with the sequence when n is got a, you know, domain of all positive integers. So they're redundant. We have 1/2 the natural log of infinity squared plus 3 minus the natural log of 1 plus 3, well, you know, whatever, that's infinity. So when we take the definite integral of f of x, we get infinity. The definite integral is increasing without bound, so thus the definite integral diverges, and therefore the given series diverges. Bam! And that is the end of our first example. Example number 2 coming up right now. And for example number 2, we have the series of natural log of n over n to the 4th power. Well, and over here I've got the convergence. That's just a summary of what I said with our issue at the end of that when we were doing our checks. The convergence or divergence of a series is not affected by deleting the first n terms. If all conditions are met, for all x which are greater than or equal to n which is greater than 1, you can use the integral from n to infinity of f of x dx to test for convergence. So having to delete or having an issue with your first couple of terms there, like we had with the first derivative not being negative until x was greater than or equal to 2, is not an issue. So let's make sure, a little extra coffee to keep me going here. Let's make sure that it's not a waste of time to apply the integral test with our problem here. In other words, let's do the nth term test. The limit as n approaches infinity of the natural log of n over n to the 4th. We're going to have a very similar expression later on in this example. I'm just going to show all this work once. We look at this and we let n approach infinity. Well, that's going to be infinity over infinity, which is a form of indeterminate, a form that allows us to apply L'Hopital's rule, which means, you know, can we take a derivative of the numerator and denominator separately and get this into a format that will more easily allow us to evaluate the limit? So we have the limit as n approaches infinity. I hope you're really very comfortable with that by now, since we're talking about series and sequences. But the derivative of the natural log of n is 1 over n. The derivative of n to the 4th is 4n cubed. And we can clean that up, but again, all we care about is finding the limit as n approaches infinity. So 1 over infinity is 0. Over infinity to the cube power is going to be infinity times 4 is infinity, which is 0 over infinity, which is 0. So again, this doesn't determine if this converges, but since it's is equal to 0, then we have the possibility of that series conversion. If that were 2 or 3 or something like that, where it wasn't equal to 0, we'd be guaranteed that this diverges, and continuing on would really be a waste of time and effort. So, yes, we might be converging. Awesome. All right, so we're going to let f of x equal the natural log of x over x to the 4th. F of x needs to be positive, it needs to be constant, and it needs to be decreasing. Well, when n is starting at 2 and going up, we're guaranteed that this is going to give us a positive answer. This is undefined at 0, but I don't really care about continuity at 0. I care about it from 2 and beyond, so we have a positive continuous function. All we have to do is make sure that it is decreasing, or at least non-increasing. And we're going to do that by looking at the derivative. So we have f prime of x is equal to Lodi high minus Heidi low all over low, which is going to be x to the 4th squared. Now that means that we're going to have a common factor. Well, let's clean this up a little bit. X to the 4th over x is x to the 3rd minus 4x to the 3rd, x to the 8th. Now the numerator both terms have a constant or common factor of x to the 3rd, taking that out. The benefit of cleaning this up a little bit is not so much, I don't need to find out when the numerator is equal to 0 or do a lot of tremendous amount of fancy calculations or algebra, but if it seems like there's a lot going on in the numerator, so much so that I can't look at it and automatically tell that it's, always positive or always negative. The denominator is x to the 8th, or now it's x to the 5th, but x is really going to be need to be greater than or equal to 2, so that's always going to be positive. We need to see when or if the numerator is always, negative. So I just want a simpler numerator to work with. So when is f prime going to be negative? When is this function decreasing? Well, we have, again, 1 minus 4 times the natural log of x needs to be less than 0. So now we have negative 4, natural log of x is less than negative 1. Now we have natural log of x is less than 1/4. Making both sides an exponent of e, and we have x, whoops, divided by a negative number. Yeah, switch that sign. So we have x needs to be greater than e to the 1/4, which means x needs to be greater than 1 point something right off the top of my head. Dun, 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 dun. Wrong page. Or is it? Ah, there it is. X needs to be greater than 1.284, which means x needs to be greater than or equal to 2, because really we're trying to emulate that idea that the domain for integers are all positive integers. So really we care about x being greater than or equal to 2. So this means that, one more time, f is continuous, it is always positive, and it is decreasing as long as x is greater than or equal to 2, which means that we can apply our interval test. Okay, which means that we need to look at, let's just put it over here, I guess, the definite integral from 2 to infinity of the natural log of x over x to the 4 dx. Now we're looking at the definite integral from 2 to infinity of x to the negative 4 natural log of x dx. That is going to require integration by parts. And when setting up your integration by parts, you're looking for the part of your integrand that is most complex that you can still integrate using a basic integration rule. And not too sure about easily integrating the natural log of x, but we can integrate the x to the negative 4 dx, and we can take the derivative and get a simpler term when we're taking the derivative of the natural log of x. So we're going to let u be equal to the natural log of x, there where du is 1 over x dx. Our dv, x to the negative 4 dx, integrating both sides to find our v, and we have v is equal to raise that power by 1 and divide by it. Yeah, and that's it. Okay, so we have, now again, I don't want to change the lower and upper limits if I don't need to, so I'm going to pull this off to the side and just start from scratch and say the indefinite integral of x to the negative 4 natural log of x dx is equal to, well, uv, so uv, I'm going to keep the negative up front, on top, or whatever, negative natural log of x over 3x to the third, so there's my uv minus the indefinite integral of v du. Okay, cleaning that up a little bit, I'm going to bring the negative 1/3 out front. X to the negative 1 times x to the negative 3 is x to the negative 4. All right, integrating again. Now I can see that we're going to have a denominator of 9, and I'm going to bring this x to the third down. So I'm going to go ahead and multiply this first fraction by 3 in the numerator and denominator, and get negative 3 natural log of x. That's going to be minus 1 over, and we have 3x to the, well, it's going to be 9 now, right? See, I don't just show this work for you guys, I need it too. 3 times 3 is 9. We have 9, x to the third. Okay. So that means, let me just make sure I haven't written something incorrectly. Beautiful. All right, so that means that we've done this indefinite integration. So this is equal to, okay, so now plugging in our infinity, we've got okay. Now, a couple of things here. Let's go ahead and sort of factor a negative 1 out of the two terms here in this numerator. And negative times negative is positive. And I'm looking over here, probably maybe should use some limit notation since this is kind of infinity over infinity. But like I said on the previous page, or that I erased, when I wanted to find out the limit as n approaches infinity of this, and I was doing that whole L'Hopital's thing, that's really kind of what's going on here. Basically what we're doing here is the limit as n, not n, but x approaches infinity of negative 3 times the natural log of x minus 1 over 9 x to the third. And we kind of need to look at this term separately and see if it approaches infinity or some kind of constant or 0, you know. And again, I don't want to show that L'Hopital's rule again just because of time, but we are going to have this kind of very similar situations. We add up here natural log of x over x to the fourth. We have a natural log of basically x, only now it's over x to the third. That denominator is still going to grow faster than the numerator. And L'Hopital's rule will show us again that that is going to be 0. So really our final answer here is 3 natural log of 2 plus 1 over 2 cubed is 8, and 8 times 9 is 72. That is a real solution, not like an infinity or negative infinity. So my definite integral converges. And the integral test said that, you know, either both the series and the integral diverge, or both the series and the integral converge, as long as you've met the requirements of doing the integral test, and we did. So therefore, since this is a real solution, the given is not one word. There, that's not your given series. There you go. That converges. And that is the end of our second example. It's really the end of the major example. I'm going to just do 2 more up here, showing you that it's going to be very beneficial to do that nth term test and make sure that you do meet all 3 requirements of the integral test before you actually apply it. Bam! And for our last 2 examples and an update of what's going on with the camera equipment, I do believe the Nikon D7000, at least audio, some issues are going on. Sound quality so far is great with the camcorder, playing with the lighting to try and make it match up with this camera a little better. So again, any feedback would be good. I think I'm going to just have to keep using my camcorder for a while. At any rate, you just care about the math, right? We have, I mean, that's what we're here for. So we have this, this series, and did it all, you know, can we just almost immediately determine if it diverges? Well, is the limit as n approaches infinity for n plus 5 over n minus 1, is that equal to 0 or is it not equal to 0? Dividing the numerator and denominator by n, we get the limit. We could probably see the answer by now with all of our awesome calculus skills, but we have 1 plus 5 over n over 1 minus 1 over n, and that certainly is going to approach 1, which means that it's not equal to 0. So the given by the nth term test the given series diverges. Now over here, if we let a sub n find the limit as n approaches infinity of a sub n, this is going to have a numerator where the numerator stays bound between -1 and 1, and the denominator is going to grow without bounds. So the limit as n approaches infinity for a sub n here, that is going to be 0. So this sequence, or the series, excuse me, may converge. But remembering that when we say let f of x equal cosine of x over 2 to the n, f needs to be positive, continuous, and decreasing. Our denominator is always going to be positive, with a positive base of 2 being raised to any number, but the numerator, y equals cosine of x, and there's nothing else going on up here to make it more complicated. The cosine of 0 is 1, the cosine of pi over 2 is 0, the cosine of pi is -1, and so on. You know what the cosine function looks like. It's going to alternate between being positive and negative. So this function is not going to always, f of x is not going to be positive for all n greater than or equal to 1. And that is our last two examples. I'm Mr. Taru. Thank you for sticking with me through the technical issues. Yeah, that's your integral test. I'm Mr. Taru. Go do your homework. I said Mr. Taru twice. Now 3 times.